and go ahead.
All right, great. Thanks, Stefano, for inviting me. Good to have a man on the inside. So thanks to all of you for coming. It's great to see everybody. What I'm going to talk to you about today generally falls under this rubric of what I've been calling the virtue of complexity. So there's kind of a complex configuration of projects that are in this on this topic that I'm working on. This was the first one. It's sort of the most well-developed now, and I think it's a good way to get some introduction into what thinking about things through the lens of complexity is actually going to get you. But let me give you a little bit of motivation and tell you what I mean by complexity. All right. So, I'm almost exclusively an empiricist. I've been working a lot on machine learning methods applied to asset pricing problems. Right? So the finance literature has recently seen some, I think, important advances in the benefits of machine learning methods for things like return prediction, factor modeling, and so forth. Okay? So the empirical gains, like out of sample, I think quite realistic empirical gains, are quite large. But there's also a lot of pushback on this literature. And I think a lot of this pushback sort of is grounded in a skepticism of using big models, about using big models. Right? I think that's kind of a healthy skepticism. So we were all trained, especially starting to become part of this older generation, we're all trained with this philosophy of parsimony, like very strongly underpinning our econometrics view of the world. But I've actually recently come to sort of seriously reevaluate that view and think that that's actually a really destructive view. Okay, so that's going to be the whole point of this paper. That's why I'm calling it the virtue of complexity. All right, so why do I think that there's kind of pushback and skepticism about using big models for empirical applications in finance and economics? Part of it is because we don't have a lot of good theoretical understanding of the properties of these models. Okay, statistical properties. We don't have a lot of theoretical understanding. That's new for economists. Economists are so used to thinking about econometrics like with really well understood, well developed theoretical properties. Okay, our colleagues over in the econ department have spent so much time like helping us understand things like time series models and the properties of estimators in those worlds. Those are small models, right? We're able to derive properties of those models, understand statistical behaviors when the models are small, when the parameterization is sparse relative to the number of observations we have. But what I'm going to argue is that that's actually just really far from real-world scenarios. Real-world scenarios when it comes to finance and economics are going to be characterized by the opposite structure, which is we have very few observations, but it's a very complex world. In principle, we're probably going to need many, many parameters to get realistic descriptions of the environments that we work in. All right, so this is actually a statistical theory paper. What I'm trying to do in this paper is actually lay out some of this foundation that will give us a better theoretical understanding of the properties of these big models, these machine learning models, these highly parameterized models. If we have a better understanding of the statistical properties, hopefully we'll face less skepticism as we go to apply these models. We'll trust more what we can learn from these models in the empirical analyses. All right, so that's what I'm going to do in this paper. I'm going to give you a theoretical analysis of machine learning models applied to finance. All right, I'm going to be emphasizing this idea of high model complexity. Okay, so what do I mean by high model complexity? Complexity is just going to be defined as the number of parameters relative to the number of observations. Okay. Now, for those of you that are a little bit familiar with the sort of machine learning literature, you'll understand that in the past 3 or 4 years, there's been this really important and fast-growing literature on this topic that goes by a couple different names. One of them is benign overfit. This idea that these very complex models, sometimes they're called over-parameterized models. Parameters space is much bigger than the space of the observations. These models actually work really well out of sample. Okay? This was actually prompted by the machine learning literature doing things like an image analysis with huge neural networks. Okay? Estimate these huge neural networks, get a training fit that's perfect, and the model still works well out of sample. That's really shocking, right? We usually think that if we get a perfect training fit, we've badly overfit the model. Right? This is what we would expect to have happen when we have a lot of parameters relative to the number of observations. Right? This whole philosophy of parsimony that's sort of underpin our econometrics, our training, would suggest that, if you have t observations and you try to use t parameters, you should expect the model to do badly on a sample. So I'm going to show you some analysis of these types of environments. I should show you that big models are going to be doing better under a lot of plausible conditions than a simpler parsimonious model that is kind of like used to the specifications we've thought.
So can I ask a question which is kind of deep broader, it's not taking a question on this, but one of the advantages of parsimony was also, forget one second about statistical, which is kind of the focus of your paper, statistical performance. But one of the advantages of parsimony is that it was kind of a bit easier to link it than to economic mechanism, right? So basically, if I think of the economics of a problem, I could say, well, maybe I don't want a very rich, well-performing statistical description of the world. So because I really want to focus on, my model will be imperfect, but will capture the economic mechanism.
Yeah.
And so how do you think about this tension?
Yeah. So I think about it as, if I'm really interested in learning something about a specific, like very precise type of mechanism, right? And I can design an empirical analysis to hone in on that, there's probably hope for using small models to understand that, right? But I actually think that type of design problem is really hard in practice, okay? So I would kind of answer it two ways. I think there are a lot of empirical problems where that's not the focus. Those are the problems that I spend my time on mostly, things like portfolio choice problems. That I actually don't really care a lot about the mechanism. I care a lot about the forecast accuracy. But then there's this other question, which is not really my research area, but is a very important topic, which is how can I actually design empirical structures if I know that there are all these kind of complicated behaviors that describe real-world phenomena, and I try and hone in on like a parsimonious description. Anyway, thanks.
I don't mean to derail you, but where does the standard question in this kind of literature fit in? The standard question is, in old-style econometrics, we begin with a hypothesis, and then we test it. In machine learning, you sort of let the computer look for hypotheses, and it finds one that works, and then, of course, the problem is, well, if you look at enough hypotheses, one of them is bound to work. Is that related to your big parameter space idea, or is it a different idea?
Yeah, so there are going to be ways that you can take some of these methods and kind of formulate hypotheses tests out of them. That's actually not going to be the approach that I'm going to be taking here. So I would kind of characterize the bifurcation a little bit differently. So one is hypothesis testing, and the other is prediction. Okay? So when I think about machine learning, I'm thinking about sort of optimizing prediction. It's not about seeking hypotheses, right? That's not what machine learning is about from my point of view. I'm not trying to learn theories that I then want to go test. I'm just trying to optimize prediction, all right? So
I don't see the difference. I mean, if you have a model that's explaining the data, then with counterfactual data, it's making a prediction. So isn't prediction and isn't a hypothesis and a prediction the same thing? If you have a hypothesis, you can make a prediction. If you can make a prediction, there's a hypothesis behind it.
Perhaps.
Maybe not. I haven't thought about this, but
yeah, perhaps. It's not really going to be a question I'm going to engage with.
Okay. Thanks.
Yeah.
What about causality? How does machine learning deal with that? Like think about simple examples. You see central banks intervene in crises. So you could come up with a conclusion from machine learning that central banks cause crises, which is not true.
So there's actually I'm sure you're somewhat aware of this, there's a very active literature on machine learning and causality. In fact, this is the sort of place where economics has sort of bought in most to machine learning. This is, again, sort of different from what I'm doing here, right? We're going to be working in kind of pure prediction context where the causality is not like a core part of the problem, which I think of as kind of like most of asset pricing analysis. Okay, so in any case, where am I going to go? I spent a lot of time on introduction because I think the motivation for this problem is important, and because it's quite different from the way we often approach these things. But let's start moving into the results. All right, so the main theoretical result that I'm going to show you is here, this idea that as I increase model complexity, I'll show you that under general conditions, things like Sharpe ratios of optimal portfolios based on those predictions improve. Okay, it's a very general result. Anyway, that's where I'm going with this. Okay, Last place I'll go is to the empirics. So I'm going to show you that a lot of these theoretical results that we've derived, they actually bear out very clearly in the data. It's sort of a standard asset pricing empirical topic. All right, so let's start with the environment. The environment's going to be extremely simple, okay? So I think this is the clearest way to start thinking about these issues. We're going to start really simple. We're going to have a linear prediction model, right? So I'm going to have a single asset that I'm trying to forecast, right? If we want, we can generalize this to cross sections of assets and so forth. I'll be going through the setting with a single asset. I'm going to be imagining the problem of forecasting the return on that asset with a collection of predictors. I'm going to have P of these predictors, all right? And the idea is that P is going to be a very big number. I'm going to have a linear specification, all right? But that linear specification, as we'll see not too far into the future, is sort of neither here nor there. We can think about this as actually covering a lot of nonlinear specifications like neural networks, all right? I'm going to try and understand the properties of this type of model when I do things like least squares estimation, when I have P being very large relative to the number of observations, okay? Now, underneath all the sort of pictures I'm going to show you, there's going to be some theory. It's going to be Brehm matrix theory-based results, okay? In order to derive some of those results, I'm going to put some conditions on the beta, right, the predictive coefficient. I think these conditions are actually not very controversial. So first of all, I'm going to assume that the predictability is identically distributed across signals in expectation. So what does that mean? What that means is that when I go to set up my problem, when I go to put in S into my prediction, I think that all of the S's are plausible predictors. I don't have a view that I'm putting some crap predictors in with some really good predictors, right? So this is just saying that kind of the econometrician has done a relatively good job of setting up their prediction model. All right? Now, this is a simplifying assumption that makes some of the theories that I'm going to derive kind of tractable, but I do think it's actually a very plausible assumption for real-world research. All right. Second, I'm going to assume that the total amount of predictability is fixed. Okay, so we're going to be doing things like taking limits as P goes to infinity, right? But if I'm not careful about that, and I don't have the predictability spread out more and more across predictors, so keeping the total amount of predictability fixed, think about the total R squared, and that the total true R squared in that predictive regression needs to be fixed. If I don't do that, I'm going to be producing infinite Sharpe ratios. Okay? In the true data generating process, I have infinite Sharpe ratios. So in order to rule that out, as I increase the number of predictors, that predictive content needs to kind of get spread thinner and thinner, holding the total predictability fixed.
Brian, does that mean, though, that you could get away with fewer predictors, though, and you don't need complexity? Like, it seems like it's pushing.
So whether you need more or fewer predictors is going to depend on the properties of the predictors, right? So if this assumption on beta is actually plausible, that all of the predictors are reasonably good ex ante, like I think they have a good chance of showing up as being predictive, then whether or not I need a lot of predictors or not is actually going to boil down to the covariance matrix of S. Okay? So think about it as if I have a lot of concentration in S, it's like saying that maybe I don't need so many predictors. But if the eigenvalues of the covariance matrix of S is they're really spread out, sort of evenly distributed, then I'm going to need a lot of predictors. So this boils down to an empirical question. A lot of the statements about what you should expect in terms of these large model limits boil down to a dependence on what the covariance structure of the S is like. Okay?
So is the assumption that as P increases, those eigenvalues get more spread out? Is that what that total predictability is fixed assumption is?
So I'm not going to make an assumption on the distribution of eigenvalues in the covariance matrix of S. I'm going to show you some results where I've essentially assumed, I'm going to show you basically a calibration where I've assumed that all of the predictors have like some independent predictive power, so it is sort of evenly distributed. If I had a data generating process where the predictive content was, say, concentrated in a couple PCs of the signals, then the theory results would look different. Right? The theory says exactly how that eigenvalue distribution maps into what you should expect for out-of-sample predictive R-squareds, out-of-sample Sharpe ratios, and so forth. All right, so this is going to be the predictive model that I'm working with, all right? Once I have a predictive model, the way I'm going to start thinking about it in terms of finance applications is just to ask, what would a portfolio do that used this predictive model? And the way that I'm going to do that, because I'm in this single asset setting, the easiest thing to do is just think about a timing strategy, right? And the timing strategy is going to be extremely simple. I'm just going to build my expected return from the prediction model, right? And I'm going to scale my position in the asset up or down in proportion with that expected return. Okay, so why do I look at this timing strategy? This is a really easy one to analyze theoretically, but it's also a realistic strategy. I mean, this is kind of close to the optimal unconditional max Sharpe ratio strategy when you have predictability. It's only off by like kind of a scale factor. All right, in any case, none of the results that I'm going to show you are going to be sensitive to the details of this trading strategy. It's just a nice, simple one to look at. All right, so that's kind of the prediction model, the portfolio that I'm going to build based on the prediction model. Now, what am I going to try and accomplish with this? So the objects that I'm going to characterize are the expected out-of-sample behaviors of those portfolios and those predictions that I just showed you. All right, so I'm not going to try and describe what's going to happen in sample at all. That's sort of exactly opposite of the point when we're using these big models. We want to understand the reliability of these things when we estimate them in sample. If you have a lot of parameters in sample, you're just going to fit really well in sample. What we care about is whether or not that fit actually deteriorates dramatically when we go out of sample. All right? Okay, so all of the objects that I'm going to show you are going to be about expected out-of-sample objects. All right? So I'm going to really emphasize what happens when P is very large relative to T. All right? When I have many more parameters than the number of observations. Along the way, it's going to be important for my conclusions whether I'm thinking about correctly specified models or incorrectly specified models. All right? Now, I think that the misspecified model case is the important and relevant one. Right? We're not going to really know how to correctly specify a model. But these types of characterizations in the correct specification setting, they're going to be good benchmark cases for us to be thinking against. All right, so we're not going to go through the theory derivations. Instead, just let me tell you that we're taking joint limits as T and P diverge, okay? But I want to be thinking about these limits where I have model complexity, all right? So I'm going to think about model complexity as C being non-zero, right? C is just bigger than 0. It might be a lot bigger than 0, okay? Understanding the complexity of the model is going to be key for me to understand the out-of-sample behaviors of these guys. All right. Okay, so the last thing that I need to tell you about before I can start showing you some of the properties of these estimators is to tell you what's going to be my estimation approach, particularly when I have a lot of parameters. So simplest place to start would be to study least squares, but least squares is only something that I can deal with when I have T greater than P. Okay? So I need to have a way to start thinking about this linear prediction model estimation when P is potentially bigger than T. So immediately I need to do something. There are a lot of different things you could do. I'm going to study ridge regression. All right? The reason why you want to study ridge regression is because ridge regression has a very tight mapping to random matrix theory. There are a lot of existing results that you can kind of take off the shelf there. Other reason is that it's going to be kind of baked into the most natural high dimensional analog to least squares that you could think about. So let me tell you a little bit what I mean about that. All right, so if I have more predictors than time series observations, this inverse starts to be degenerate. All right? If I just add an identity matrix with a little bit of penalization Z to it, all of a sudden that inverse starts being well behaved again. Okay? So this is ridge regression. A really interesting case to think about is what happens when I sort of stick in this infinitesimal Z. All right? So I just need a little bit of Z to make that inverse well behaved. Okay? So this object the limit of this inverse as z goes to 0, right? We're going to call this ridgeless regression. It's what you do when you want to be as close to, as possible to least squares, but you can't really do least squares because you don't have enough data. All right? So that object study, we'll call it ridgeless regression. All right? So if I do have enough observations, ridgeless regression is just OLS. If I don't have enough observations, there's another way to write this limiting estimator. Okay? It just uses the pseudo inverse, okay, of the covariance matrix. Now, if you think about what this ridgeless estimator is actually doing, it's saying, just think about it in terms of linear algebra. You have t observations, p unknowns, okay? So you're solving the system of linear equations, it's underdetermined. There's an infinite number of solutions for beta, okay? How do you pick a solution? When I take the limit as z goes to 0, what I'm doing is I'm actually just picking the solution with the minimum L2 norm. So I'm actually doing infinitesimal ridge penalization, but I'm still picking a solution that's kind of well-behaved, it's kind of regularized, it's sort of shrunken, right? Because it has the minimum L2 norm of all the possible solutions. So this is an interesting idea. This ridgeless regression is going to have some really cool properties when we start to make p, the number of predictor variables, really, really large, okay? So I'm going to focus a lot on what happens in the ridgeless regression case. These statements that I made, like Sharpe ratios are going to be increasing in model complexity, will be true even with ridgeless regression, right? If I add additional non-trivial shrinkage, it could be even more true, okay? Additional shrinkage could help as well. That sort of depends on the exact context that you're in. All right, so that's the environment. From here, what we're going to do, I'm just going to start showing you some pictures that describe sort of the properties of this estimator according to the theory, these expected out-of-sample properties, as I vary things like the number of observations p, the amount of shrinkage that I do z, and so forth. All right. So as a starter, this theory can tell us what happens when we do OLS. All right. So when we do OLS, we're talking about the setting where c, complexity, right, is less than 1. I have more observations than I do parameters. All right, now if c is 0, and of course p and t, all these results have to be limiting results for me to make these characterizations, but if c is 0, that's kind of our standard econometrics, right? Those are our asymptotic behaviors. There we get everything first best, right? We get the true R squared gets recovered from our model, right? The behavior of the beta, its variance is going to be sort of well controlled. All right. Now, what happens as I start to take model complexity a little bit away from 0? So this is saying that the number of parameters is growing with the number of observations. It might be growing like a proportion less than 1, but it still means that as I go into very big data settings, I'm still going to have very big models, right? In that case, I can still do ridgeless regression, which is basically going to be shown with this dark blue line here. But as long as p is growing with t, so that my model complexity is just anything bigger than 0, the out-of-sample behavior of OLS starts to deteriorate. And of course, as I get to c close to 1, as I get to this point where the number of observations is moving 1 for 1 with the number of parameters, right, then that's going to be kind of the worst case scenario. Because OLS is going to be degenerate. Its R squared is going to diverge very negatively, right? But at the same time, ridgeless regression doesn't kick in yet because I still have a unique solution to that system of equations.
So why the R squared is negative here?
Why is the R squared negative? So in sample, I've estimated OLS, right? I have many parameters. This inverse matrix in OLS is sort of ill-conditioned. When I go out of sample, it essentially over-predicts in a way that produces a negative R squared. Maybe the best way to see this is actually to look at what happens to the norm of the beta estimates, really the variance of the beta estimates, as complexity goes up. So as complexity goes up, what happens is that the variance of the beta is getting bigger and bigger. You just don't have enough observations to come up with a sensible beta estimate. all right? And that's what's giving you the big negative out of sample R squared.
And what is the scale of this norm? Like when we see 8, what?
So here, the norm of beta, it's actually on the order of like 0.2. That's like what we have in the true model here. The exact magnitude is just a calibration that I picked, but these general patterns hold, right? Okay, so that's kind of about like background, what happens in OLS when I start to have too many parameters. Right. Now, here's what's really interesting. I want to think about what happens if I go to the other side of 1. If I start to really push the number of parameters past the number of observations. Okay. Well, when that happens, you're going to see that actually the R squared starts to recover, right? The beta norm starts to come down. This is actually very closely related to what the statisticians call benign overfit. This idea that when I go into what we would call an over-parameterized setting, I have P much bigger than T, say maybe 10 times bigger, that these R squareds out of sample actually behave reasonably well. All right, so why is this happening? It's happening because ridgeless regression is implicitly shrinking, right? So, right, if I have this environment where P is bigger than T, I have many betas that exactly fit the training data. They all give me an R squared of 1 in sample. They exactly fit the training data. But they also do pretty well out of sample too. And that's exactly what the machine learners saw that got them thinking about this topic. They saw that they would actually do this with their neural network models, right? They get perfect training fits and good out of sample fits. All right. Yeah, go ahead.
Isn't R2 just a wrong metric to look here? And that's actually just
R2 is the
lowest squared. So for example, if you get negativity of the R squared, just because the variance goes up.
So I think that, yeah, R squared, not important. I mean, statisticians wouldn't look at R squared anyway. They look at MSE, right? Okay. The point is, MSE comes down, right? When I have MSE shoots up when I get to a C around 1, and then it comes back down again, like it did close to 0, right? That's what we are talking about when we're talking about the idea of benign overfit. I have a very big model, but it still pulls down my prediction error out of sample.
So is it, I don't know how to read this, but if you do nothing, if you just like predict with a constant, are you on the left axis?
Okay, so
I'm just wondering, it seems like all the lines improve, but they stay below 0. So like, wouldn't you just be better off doing nothing?
yeah, so this is kind of related to Alay's question, which is, in some sense, the R squared makes like a scaling choice that's kind of irrelevant. What's negative and what's positive doesn't really matter all that much. So why oftentimes a statistician wouldn't even care about R, they just pay attention to MSE. How close can I get that MSE to 0, right? So if I have a constant in here, right, that would be similar to a very small model like C equals 0. I'm talking about, by the way, the correctly specified case here, okay? So now, I guess I should be a little bit clearer about this. As I increase model complexity, what am I actually doing? I'm making the true data generating processes model bigger and bigger, okay? So the true DGP has lots and lots of predictors in it, and I'm always estimating an empirical model that aligns with that DGP, and I'm just saying that even when I have a correctly specified model, this thing does really poorly if C is around 1. But if I push C well beyond 1, the correctly specified model suddenly starts to behave better again. Now, why is this happening? It really boils down to this kind of simple implicit regularization point of ridge regression, or ridgeless regression. Right? When I have an over-parameterized setting, I have lots of possible beta solutions I could use. I could pick the maximum norm beta solution. It would do horribly out of sample. But the natural analog to OLS is to use the pseudo-inverse in that calculation. That's equivalent to this limiting bridge regression. And that thing actually does well out of sample. So this is a phenomenon that people have been talking about in stats for like 2, 3, 4 years, right? What I want to do in this paper is really ask, what does this imply for finance? Okay, so that's where we are now. I've sort of set the stage based on thinking about things in terms of predictive performance. All right, one thing that I want to point out, all right, and this kind of goes back to my motivation. sort of challenges the dogma of parsimony, right? What it's telling you is that you can achieve high forecast accuracy even when you have big models, all right? So I want to start to think about that point and take it more seriously. And to take that point seriously, we need to do a couple more things. Go ahead.
Could I pursue my previous question? When you go to the limit and you let the number of parameters rise as long as with the amount of data, each time the parameters rise, you're changing the model. It's not the same data generating model. So isn't there some implicit assumption you're making that makes all the new variables just as important and just as reliable as the old ones?
Yes.
And isn't that driving a lot of the result? I mean, when you so if you do this in practice, you can use a low-dimensional neural network, and then you could start adding, different layers, and the functions get more complicated. They're all nonlinear, by the way. I don't know what linearity and nonlinear, but anyway, that's an aside. So the new functions you're adding are just much more esoteric and complicated than the original ones, and I'm wondering whether it makes sense to suppose that they're as likely to be as important as the original ones.
Okay, so whether or not you want to suppose that they're as likely or less likely to be as significant as the original one is an interesting question. It's actually going to be really closely related to neural nets, right? But I need to delay that for a moment. What I do want to recognize is that you're totally on the right track. Just thinking about this is not the right way to be thinking about the properties of these models. Because what does it really mean to have the true data generating process getting bigger and bigger, right? There's no empirical counterpart for that. There is a true data generating process, and then we have empirical models that get bigger or smaller, right? That's exactly what I want to be thinking about when I move to the misspecified model environment. And that's where all of the most important conclusions show up, okay? All right. Okay, so these are statements about statistical properties of essentially ridge regression in a high-dimensional setting. What I want to think about next are what happens in finite, okay? So how about the expected return of my model as a function of model complexity? How does that thing behave? Well, this is kind of interesting. If I have a ridgeless regression, so I'm doing minimal regularization, I have C less than 1, so I'm doing OLS. It doesn't matter if my model's big, right, relative to the number of observations. C might be a half or 0.9. I'm still actually doing a recovery of the true ER. Why? Well, that's just about the unbiasedness of OLS, okay? OLS is unbiased. My expected out-of-sample ER is going to be the true ER, right? Even if C gets very close to 1. Now, if I start to get into a situation where the true data generating process is big relative to the number of observations, well, now I can't do OLS. It's just not on the table. I can do ridgeless regression, but ridgeless regression uses shrinkage. And you see that here. As I increase complexity, my ER, even in the ridgeless regression case, starts to deteriorate. Why is that? It's because once I get out here, I have to start using that limiting type of shrinkage. Right? Now, why does the ER deteriorate more and more as the true DGP gets bigger and bigger? Because the space of solutions grows as the model gets bigger. Right? If I have P even bigger relative to C, the space of betas that give me a perfect in-sample fit has grown. I can find a lower norm beta. Okay? So implicitly, even before I start doing ridge, even with infinitesimal ridge, I get this property that shrinkage starts to eat into the ER in a high complexity setting. Now, that's sort of the downside of shrinkage. The upside of shrinkage is that the variance starts to get controlled. My trading strategy's volatility also tails off due to that shrinkage. Right? Now, volatility, R squared, beta norm, these are all essentially the same objects. It's just telling you how volatile your estimator is. And the surprising fact, I guess, is that as complexity gets very big, even with ridgeless regression, the volatility of your estimator is controlled. Right? Now, at this point, we have something I think pretty cool teed up, which is I have a deterioration in the ER in a high complex model, but I also have a reduction in volatility, right? So if I'm a trader, what should I do? It's not at all obvious. It depends how those two trade off, right? It depends about the Sharpe ratio. So let's look at the Sharpe ratio. This is the behavior of this timing strategy Sharpe ratio as I vary from very simple models to very rich models. Note that in all cases, the Sharpe ratio is positive. Why is that? Because I'm doing OLS, it's correctly specified, the ER is going to be positive. Right? It's just a quadratic object, it's always going to be positive. The behavior of this Sharpe ratio is going to be critically impacted by the volatility of the trading strategy. Where does the volatility of the trading strategy blow up? At a complexity of 1. And that's where you see ridgeless regression deteriorate. But actually, anywhere away from there, the amount of shrinkage that you do sort of doesn't matter, right? If I have a very small model, if I do a little bit of shrinkage, a lot of shrinkage, I still get the same Sharpe ratio. If I have a very large data generating process, I do a little bit of shrinkage or I do a lot of shrinkage, I still get the same Sharpe ratio. Why is that? Because the Sharpe ratio is scale free. I've reduced the ER, but I've also reduced the volatility. And it turns out to be the case that this bias variance trade-off nets out in terms of Sharpe ratio. So that's an important implication for thinking about finance and where complexity comes into play with our applications, right? If you're in the statistics realm, you care about model fit, model accuracy. That's very much about the variance end of things. This trade-off is an interesting object that we want to be thinking about when we're talking about our finance applications.
Sorry, before you move on, so this kind of suggests that you kind of want to have more shrinkage in general. It seems like, maybe I'm not seeing the curve correctly, but it seems like when you do some shrinkage at least, you still do better doing no shrinkage, right? Even when you go with high model complexity. Yeah. Is that general result?
So generally speaking, more shrinkage improves the behavior of the estimator. I've been focusing on the ridgeless case because I think the interesting statement is even with minimal shrinkage, these estimators behave well. Yeah. But adding additional shrinkage improves.
So I guess the advantage is that in general, in a practical application, you don't know what C is, right? Mm-hmm. So with the blue, with the bottom line, you might have.
You are very sensitive to it, right? Exactly. And if you set your shrinkage to some high level, like 1,000, you're going to be doing well regardless of C.
So the limit of the high shrinkage is what? You get the identity matrix as your to invert, right? So is that well if you just beat that?
Right. So that's sort of like if we were thinking like about a factor set, it would be like an equal weighted average, right? So it's basically no variance modulation in your strategy. Yeah.
And what is so special about C equal 1? Why things go bad?
So what's special about C equal 1 is that's the point at which your hands are tied. You have a unique solution to the least squares problem, right? But that unique solution corresponds to a very high variance beta estimate, okay? So you can do something there. You have to use non-trivial shrinkage, right? But that's the point. That's the one case where ridgeless regression doesn't really help you, okay, where C is close to 1. All right, so now coming back to John's question, we can talk about correct specification versus misspecified models. So what I did was I went through the correct specified case because I think that's always the right place to start to understand the properties of these things. But what I'm really doing is like showing you these theoretical comparative statics where I start with the true model being really small and I vary it to a true model that's very big. And I allow the empirical model to go 1 for 1 with it. It's always correctly specified. But that sort of leads to some misleading conclusions here, right? It would sort of suggest that big models are bad, right? You have a lower Sharpe ratio with big models. But that's not true. If you have a true data generating process that's a big model, that's the only world that you can live in. If you have a true data generating process with a small model, that's the only world that you can live in. What I want to be thinking about is kind of the more informative imperative statics, is thinking about what happens when there's only one true model. And then I vary my empirical model from small to large. All right? So now I'm not thinking about the complexity of the truth, I'm thinking about the complexity of the empirical model. All right? So I'm going to start from an environment where I have a complex true model. All right? So imagine something like C is large in the true DGP. And now I'm going to show you the theoretical behavior of these objects when I start with 1 signal, 2 signals, all the way up to 1,000 signals. Now I'm going to still be going through this exercise where the signals are all kind of IID in their predictive content, all right? And we can talk about why that matters. I'm going to keep deferring that question.
Just like the other way to go is to estimate a large number of small models and then aggregate them.
And then average them, yeah. So that is interesting. It's something we consider in the paper. In the environment that we set up, that would be a suboptimal thing to do, though. All right, but it's actually a reasonably well-behaved thing to do for reasons that I know you know, which is that forecast combinations just tend to work well. Okay. All right. So the way to think about it is that when I was showing you that Sharpe ratio plot, right, there was only a cost to having a big model. As I had a bigger and bigger true data generating process, I had to make my empirical model bigger. And as I make my empirical model bigger, I have to pay the cost of estimating all those parameters. And you can think about that as where the cost of that Sharpe ratio drop comes from. So if you have always a correctly specified model, there's only the statistical costs in the comparative static. Now, if you have a misspecified model, and I vary the number of parameters, if I add parameters, I still have to pay that statistical cost of estimating more and more parameters with a fixed number of data points. But now there's an added benefit of including more and more predictors. I might be getting a more accurate approximation of the true model. And that is what is so important about thinking about misspecified model settings, is that over here, I'm going to be estimating an empirical model that is parsimonious, right? But it's wrong. It's not going to be a good forecaster. Out here, I'm going to be investigating an empirical model that's not at all parsimonious, very costly from a statistical standpoint, but it's much more accurate. So there's a trade-off here, and I want to understand what does this actually mean. So if I think about this as kind of the most important question about high model complexity for the type of stuff that I do, like building an optimal trading strategy off of predictions, that's the question. Does the improvement in approximation accuracy from using a really big empirical model, does that justify the cost that I have to pay to estimate all those parameters? Right? That's the next analysis that I want to do. So let's.
You want to go first, Paul?
So what if you go beyond where you need to go?
Exactly the same question.
Yeah, so you guys are way ahead of me. I'm going to stop at correct specification. If I go further, then I'm back to the situation where I'm paying the cost without incremental benefit. Things are going to start to come back down.
But in some sense, no, I had the same question. But the fact that if you go above the limit, right? The threshold you have there, it seems like what you have an extra signal which should not be informative about the data generated process, right? Mm-hmm. So otherwise, it would be included in the BGP.
Yes.
So this is really adding something that doesn't help you at all.
Absolutely.
So it's just a variance, right? You just get a variance.
Exactly. That's it. That's exactly the point. You pay the statistical cost variance, but you have no benefit of reduced bias. And that's another way to think about it. Stefano,
I don't have the same question because I asked the question last time, but a different question, which is, so for given P, you could potentially have many different models with the same number of parameters. So you could have a neural network versus a linear model. So how do you think about this?
Okay, so this is a difficult question, right? So this is where the assumptions at the beginning come in. The assumptions that I made allow me to sort of answer that, all right? Now, when I go to the data, this idea of how do I think about sort of democratically allocating predictive content to signals is a difficult question. I'm going to have a way of doing that, okay? What I'm going to do is I'm going to start with an information set. I'm going to shuffle it all up and spread it out into P predictors. And if I increase P, I'm going to shuffle up all of that predictive information and spread it into even more predictors, okay? So I'm constructing predictors that sort of are randomly allocating information across signals that will map up with my theory. Okay? So there was one more question. Go ahead. Yeah, I'm ahead. We'll come to that.
I'm still really confused though about, I mean, this is one notion of misspecification, which is omitted variable bias, but I feel like the concern here is lack of stationarity of the forecasting environment, and it seems like you get slaughtered with these big models in that context.
So introducing ideas like non-stationarity, super interesting and super relevant for this problem. But this is a layer of complication, like well beyond what we're going to handle here. I actually think what we're doing here has an enormous amount to say about non-stationarity, because if we think about non-stationarity, we think about shrinking the amount of time series observations we have relative to the number of model parameters that we have, right? As things get more non-stationarity, we have fewer and fewer observations to train a given model structure on. So this is going to be informative, actually, about sort of the extent of non-stationarity in the data. We could do things like look at performance of these types of estimators, these types of high-dimensional models, with different estimation windows. That's could be potentially interesting about, informative about non-stationarity. It's on the agenda.